Hello friends, it's MoNaCo here in our first video lecture for our Redox unit. At the end of this lecture, I want you to have a basic understanding of what oxidation and reduction are, how to use this mnemonic device, which is Leo goes Gur, and you'll be able to see the basics of reactions if they're redox or not by looking at them, and those are all going to be single replacement reactions. So let's get into our lead-in here. The oxidation numbers on the elements are something that we studied at the very beginning of the year. Those represent the number of electrons lost or gained by an element to become stable. So in most reactions, like double replacements and stuff, the oxidation number doesn't change. But in single replacement reactions, the oxidation numbers of the elements do change. This means electrons are being transferred between elements. Think back to that chemical bonding when we did one element losing electrons, the other one gaining. So this is kind of a review back to the beginning of the year under the new title, Oxidation Reduction. So reduction, oxidation reactions, aka redox. Reactions that involve transfer of electrons. Both reduction and oxidation must happen simultaneously. So the word redox is a simplification of oxidation reduction or reduction oxidation. The reduction itself is a gain of electrons by an atom or an ion. Oxidation number goes down, it reduces. So the gain of electrons by an atom, so for example, if I had, let's do one that likes to gain electrons. Fluorine plus 1 electron becomes fluorine -1. So the oxidation number went from 0 to -1, and therefore we call that a reduction, by reduction in the gain of electrons. Oxidation is the opposite, the loss of electrons by an atom or an ion, and the oxidation number goes up or increases. An example would be something that fluorine would like to get together with would be lithium becoming lithium +1 plus 1 electron. Okay, so that's oxidation. Now, at the beginning of the year, we kind of showed how lithium and fluorine might get together to make a formula for a chemical compound. And we said lithium is a Bohr model with its 1 electron. And we said, well, how about fluorine, Bohr model, with its 7 valence electrons? Okay, there we go. And we would circle this electron from lithium and show that it transfers over to fluorine. Well, essentially, what I've done in these equations is draw the two half reactions of what happens there. One, fluorine has gained an electron and become fluoride -1. That electron, 1e negative, comes from lithium to fluorine in this first half reaction. In lithium, it is showing us losing an electron. So both of these reactions, 1 and 2, are half reactions that occur when that single electron gets transferred in an oxidation reduction reaction. So always remember how these work by the mnemonic device, Leo, the lion, goes Gur. Lose electrons equals oxidation, right there. Lose electrons, that's oxidation. Gain electrons, that's reduction, right there. Oxidation and reduction happen because of the desire for electrons in a chemical reaction. We called this the octet rule, the desire for electrons. We wanted to make sure that all of our elements had 8 electrons in their valence shell. And so oxidation reduction occurs. Oxidation and reduction are, let's see, mutual or simultaneous. So whenever one atom loses electrons, some other atom has to gain them. And so that's why we were using the lithium example, 1 electron to lose, and the fluoride example, 1 electron to gain. So while we might draw these as half reactions or steps, that action of 1 electron moving, this guy gets oxidation is losing, Leo, lose electrons, oxidation. This one is Gur, gain electrons, reduction. So that electron, 1e negative, is gained by the fluorine and lost by the lithium. So we have Leo and Gur occurring at the same time. So this green chunk experiment, this little demo I want to show to you, it's a single replacement reaction that involves an oxidation and a reduction. Elements by themselves, by definition, have an oxidation state of 0. And when they're in formulas or compounds, they have the oxidation states that are given to them across the periodic table. If we combine aluminum with copper chloride, Aluminum is going to replace the copper because according to table J, aluminum is more active than copper. So we're going to swap aluminum in where the copper was and make a new formula. So we have aluminum, +3, with chlorine, there's 3 of them, each one's -1, and we make copper by itself. So we have a swapped aluminum and copper. So aluminum having oxidation state 0 is now got an oxidation state of +3. It lost 3 electrons. Copper having an oxidation state of +2 now has an oxidation state of 0. We do have to balance this to make sure everything works out. So we put this out there, that out there, and that right there. Balancing that equation is not the focus of this lecture. We're going to have one about doing that a little bit later to show both mass conservation and charge conservation. But generally speaking, that was a single replacement redox reaction. To identify a redox reaction, we begin to look at the oxidation numbers. And we're thinking about movement of electrons. So we want to see how the oxidation numbers in one element changes from the reactants to the product side. Oxidation number is the positive, negative, or neutral value that can be assigned to atoms used to identify how many electrons are being lost or gained by an atom or ion when they form bonds. If you look at the periodic table, let's go back to our lithium example. In the top right corner, you'd see a +1 in the lithium square. It has a 7 here and a 3 here, and it goes 2-1 over here. That's all inside the lithium square. This number is the oxidation number. That's the number lithium likes to form in compounds. So we'll be looking for those types of things to change to identify if it's a redox reaction or not. So here's a good example, carbon. It has 4 selected oxidation states. You could either lose 4 electrons, gain 4 electrons, lose 2, or lose 4. Those are the 3 options for it. The first trick is to see if it's a single replacement reaction, because these are always redox. Zinc element by itself is going to have a 0 oxidation state. When it reacts with hydrochloric acid, it makes zinc chloride, and zinc becomes a +2, chlorine's with -1 still. And the hydrogen gas that's created, because this is a metal, and this is an acid, that was our previous unit. Metal and acid makes a salt and hydrogen gas. So we have oxidation state for hydrogen going from +1 to 0. It went from +1 to 0, so it gained an electron. And then zinc went from 0 to +2, lost, well, in this case, 2 electrons. We'll show how to balance these in the future. We had to put a 2 here for that. 1 zinc chloride and 1 hydrogen gas. Okay. We'll be balancing these equations in the future. So again, the first thing you're looking for is if it's a single replacement reaction to tell you if it's redox. Trick 2, double replacement reactions are not redox. If you identify the oxidation states of these elements, sodium before, we're going to make sodium chloride after, and HOH, so H2O after. This is another acid base. There's our base plus our acid. Okay. Hydrogen is still a +1. Oxygen is still a -2. Okay. Sodium is still a +1, and chlorine is still a -1. So nothing actually happened with the oxidation states. No redox. No redox. And we'll practice this over and over so you really get the hang of it. So I want you to know at this point, basically, that oxidation and reduction relate to the transfer of electrons. The mnemonic device, Leo goes to Gur, helps you remember which is which. Lose electrons is oxidation, gain electrons is reduction. And basically, you're going to have to start identifying reaction as redox if the oxidation number of an element changes. And that's for single replacement reactions only. There's 3 pages of practice on identifying oxidation numbers in our practice pack that we are going to be working together on in class, but I'd like you to try and give it a shot. And remember, all compounds are neutral when we figure these things out. So thanks for watching. See you later.